All right, this is going to be a kind of short video. The idea is really simple. It's just if two triangles are similar, or if two shapes are similar, then every corresponding thing is similar. So yeah, similar. Every corresponding side is proportional, and that applies to any corresponding one-dimensional length. It doesn't have to be a side length. So for example, yeah, we already knew sides are proportional, but medians are proportional, mid-segments, altitudes, angle bisectors, literally anything. If I were to just go like, I don't know, 40% of the way across, and then to 50%, and then to like 60%, and then to like, if I were to just zigzag like, choo, 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 that random distance, as long as it was based on percents, so it was proportionally shrunk correctly, so it was still corresponding, the same in this one, that would be a corresponding zigzag lightning bolt, and it would be proportional in the same scale factor as the side length, same scale factor as the perimeter, same scale factor as the angle bisectors. So every single one-dimensional length is shrunk or is multiplied by a scale factor. So if everything is cut by 20%, you multiply everything by 80%, and it's shrunk to 80% the one-dimensional length. Every single one-dimensional length, no matter where in the picture you measure, it could be a zigzag, up, down, sideways, diagonal. As long as you measure the same thing in both pictures, it will always be 80% of the one-dimensional length. That's the big idea, right? Maybe you call it CPSTP for this title. You just make things up. And then there's one random theorem that we never use. We use it in this. It might show up on a quiz or a test, and then we just toss it in the rubbish bin. Rubbish! Rubbish! Oh, what am I from the UK? This is great. Okay, so every corresponding one-dimensional length is proportional. So we have some theorems. One says the perimeters are, and I'm going to prove it down below, so I won't go into it right now. But yeah, so if you have two triangles that are similar and you have like a 1:2 ratio, then the perimeter of this one being 12 means the perimeter of this one is 24 because it's in the same ratio as the sides, right? Okay. Let's go back over here. If two triangles are similar, then their corresponding altitudes have the same ratio as every side. So it goes side, 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 side. A ratio of, oh wait, the first one was altitude. So it says, oh, all these three sides have this common scale factor, and so does the altitude. And then it goes, oh, all of the sides have the same scale factor, and so does the angle bisector. And then it goes, oh, all of the sides have the same scale factor, and so does the median. Every single one. Okay. Whew. Good stuff. All right. So here's our random theorem, though, that we come across. It's interesting. So it's just saying if we have an angle bisector and a triangle, any triangle, angle bisector, there's no similar triangles here. Okay. It's just I have a triangle and I have the angle bisector drawn. Well, then what it means is these two sides are proportional. Well, not sides. This is just a piece from A to D. This piece is proportional to side AC. And the rest, dB, is proportional to this side, right? It's kind of random. We only use it in like this. It's just like a fun thing geometry teachers like to like flex a little bit, be like, look at this clever proof. But we never really use it. So here we go. Okay, here's the proof. All we do is we construct a line that goes through point A and is parallel to CD. So we just go, oh, it's passing through A, and what direction should I go? Oh, parallel. Okay, I can go in that direction. Got it, right? That was a postulate, right? Between any point not on a line, we can make a line parallel that passes through that point, because it's just saying go through location and point in direction. So yeah, we could do that. All right, so once you've made that, then here's the proof. The idea is simply that here's alternate interior angles along a parallel line, and angle bisector, so all three of these angles are the same, and corresponding angles, so 4 matches with 2. So all 4 of those angles are the same. Oh, that's kind of fun, right? If all 4 of those angles are the same, well, look at this. Then that means that this side length is the same as this. That's the base angle biconditional, or the converse of the base angle theorem. So these two sides match. Oh, now how's that useful? Well, then it's just the triangle proportionality theorem. And just because we made that line parallel, we got all 4 of those angles are the same. So then in this isosceles triangle, those two sides are the same. And then the rest is just the triangle proportionality. So what I mean is, right, the triangle proportionality theorem says A is to B as C is to D, right? So A is to B as C is to D. Or I think we chose the order being what, AD to EC. So we did these two are proportional to these two, right? And then you just substitute out the side EC for the side AC because they're the same. That's it. So you do all this work with getting those 4 angles are the same, just to get that 3 is the same as 4, to use the base angle biconditional. And once you do all that, angles are the same biconditional, the whole point of that was simply to say, well, the triangle proportionality theorem said these were proportional. Okay, I'll erase my letters. And I wrote that in purple right there. AD is to EC as BD is to BC. That's just the triangle proportionality theorem from the last video. And then since we showed by all those angles being the same that side AC and EC were equal, well then I could just swap out the EC here for an AC, and I just proved this random theorem, right? And this random theorem, again, if we go back up to the picture, just says in an angle bisector, it cuts this other side, so it cuts this bottom side down here into 2 pieces that are proportional to the sides next to them. Wow, cool, interesting, random factoid. Now let's just do homework. Okay, so first one, what must be true about these triangles before you can conclude that the ratio of this segment to this segment is the same as the ratio of this, well, let's do color matching, is the same as the ratio of BA to NN? Well, 2 things, right? 1, we must have similar triangles. Okay, so if we don't have similar triangles, we don't know any ratio between the 2 triangles. Okay, but the second thing is, now that we have similar triangles, we just need to know that AD corresponds to MR. So if we know at all that these 2 correspond, right? So for example, like, okay, they're given a triangle ABC is similar to triangle MNQ, and then we're told that, for example, I don't know, like it says AD is the median, okay, and MR is also the median, and we know AD starts at A and MR starts at M, so it's the median from the same corresponding vertex. So these 2 medians correspond to each other, and the triangles are similar, so we just need to know the shapes are similar, and somehow those items that we want to talk about correspond to one another. And if we do, well, then the ratios are proportional. That was our big idea up above. Okay, so find the perimeter of a given triangle. So it tells us that the 2 triangles are similar. So every side is in ratio. So we could do this manually, right? We could go, oh, the ratio is 5 to 3. We could solve for x. The ratio is 5 to 3. We could solve for y. Or we could more elegantly say, well, the perimeter of this is 5 plus 6 plus 7. Thus thou it is 18. I don't know. That's my intelligentsia voice, okay? But then we know the ratio, right, is 5 to 3, okay? So I'm going to go from big to small. We'll say 5 is to 3 as the perimeter of the big, that's 18, is to the perimeter of the small, so we'll just leave it as PS. Okay, and that's how you can say the ratio of the perimeters is the same as the ratio of the sides, as long as we know they're corresponding, right? So here, AB was corresponding with DE, so yes, those were the corresponding. So we could cross multiply, we go, that's 5 perimeter and a little subscript S equals 3, that's 30, and 24, that's 54. We divide, we get the perimeter of the small one must be 54 over 5. Wow. Woo, interesting. Or it's 10.8 if you used a calculator. Okay, so over here it says, oh, it's given us stuff, but it's in writing. This is much more challenging, okay? Ooh, it says the perimeter of SRT. So the perimeter of this one, which I'm just looking at WX and ST. So these 2 do correspond to one another. So this is the perimeter of the big one is 15. And we want to again find the perimeter of the small. So I'll say 5 is to 6 as the perimeter of the small one is to the perimeter of the big. And then I could just erase the perimeter of the big and say, well, I know that's 8 or 15. And then I just cross multiply. So 40, no, 75, I can do that. 5 times 15 equals 6 times the perimeter of the small. Dividing by 6, we get The perimeter of the small is just 75/6. Okay. Oh, hey, that kind of works. We could divide by 3 actually. So that's actually 25/2 or 12.5. Okay. Anyways, now we need to find x here. Well, look at this. We don't even need anything fancy. But just past section, this triangle is similar to this triangle. And so just by angle markers, we know x is to 12 because it's between right angle and double. And I'm going in this direction, as hypotenuse is to hypotenuse. And so I'll multiply this one by 2, so I'm not dealing with anything crazy on the left with decimals inside of fractions. So here's 13/20. Oh, but this is just 1/2 on the right. So x is to 12 as 1 is to 2. So we cross multiply, but we know it's 6 already. And so x is 6. All right, and this other one, oh, look at this. What do we have here? So what we have, and look at this over here. Over here we got the angle bisector. Sorry, I'm getting distracted. Okay, in this triangle we have big triangle is similar to big triangle. How do we know that? Forget all the little marking with the line in the middle. Big triangles we know are similar because A, and A. All right, so we know that. So look at that. Okay, I'm just going to write this. So triangle similar by AA. All right, and then we also know it is corresponding median, right? Because what's the definition of a median? A median connects vertex to midpoint of other side, and that's what we have. And we know it's the corresponding one because it's the vertex hitting the midpoint between the two marked angles. So those two do correspond. So the ratios of those medians is the same as the ratios of the triangles. And we know the ratios of the triangles is 16, I wrote 15, so 16 to 12 going from big to small because 16 is between the two marked angles, 12 is between the two marked angles. So that's the ratio is 16 to 12. And that's the same as the ratio of those corresponding medians. So that's 20 to x. And then I'm going to simplify on the right, dividing by 4. This is 4/3. So cross multiplying, we get 4x equals 60. Dividing, we get x is 15. Okay, and on the right, we get that funky little theorem, that funky one. We got angle bisector here, cuts this other side, and so these are proportional. That's it. It's a funny little thing. We only use it in this circumstance. So let's go 9 is to 24 as x is to 18. I should have done that the other way so I could simplify better. But whatever, let's multiply. So we got 9 times 18 equals 24 times x. I don't want to do that, so I'm going to divide both sides by 6. So I get 9 times 3 equals 4 times x. That's better. Okay, 27 equals 4x. Divide by 4, we get x equals 27/4. All right. Now let's prove that perimeter one. Okay, so if we have similar triangles with some scale factor, that's what it's just saying. Say take any two sides, they're in this ratio, right? There's no m and n in the picture. It's just saying that's the scale factor. Then show that's the ratio of the perimeters, okay? Well, another way of writing this is that side AB is equal to side DE times m over n. So in other words, that means, and I'm not writing out a technical proof here. Do you guys want, I know I'm not going to write it out. Actually, the instructions here were paragraph proof. So what that means is this side is m over n times DE. All right, and then BC corresponds with EF. So BC and EF, so this one is m over n times EF. Yep, EF. And then this one over here is m over n, that's the scale factor, times df. Okay, so the perimeter of this one is the perimeter of perimeter of triangle DEF is equal to DE plus EF plus FD. Okay, and that's just by the very definition of perimeter. And then over here, the perimeter of this one, so perimeter of triangle ABC, is equal to AB plus BC plus CA. Or using substitution, that's m over n times DE plus, and you can see what's happening here, m over n times EF, just substitution, plus M over N dF. And then we factor out the M over N from all those terms, and we get dE plus EF. And what's dE plus EF plus dF? What's that? Do we recognize that anywhere? Oh yeah, we do. That's the perimeter of the smaller triangle. So that means we now have the perimeter of triangle ABC equals M over N times, and I just substitute out this whole value for the equal perimeter of triangle DEF. And then if I just want to divide both sides by that perimeter, I just divide both sides by perimeter of triangle DEF, right? Same perimeter, triangle DEF. And look at what we just proved. We now have that the perimeter, those cancel, and so we get the perimeter of triangle ABC is divided by the perimeter of triangle DEF, and that's equal to M over N. Right? And so it was just an algebraic proof, really. I didn't write like rigorous steps, but it was all straightforward. Okay, let's do the next ones. Okay, find the perimeter of the given triangle. So we want to find the perimeter of BCD, that's this triangle down here in blue, and it tells us that BCD is similar to, and I'm going to mark the angles, so B and F and D and C, so D and C, whoops, sorry, I did D in the wrong triangle, so D in this triangle, and C in this triangle, and then E in this triangle, and D in this triangle. So those are what correspond. So I know that the perimeter of the top one is 4 plus 5 plus 8, right? That's 9 plus 8, that's 17. So that's the perimeter of the small one, okay? And then I know that the ratio of these, I know that side DE matches with side CD, so the ratio is 8 to 12 is the same as the ratio of the perimeter. So small perimeter to big perimeter. And I could reduce this on the left by 4 on top and bottom, and I get 2/3. So cross multiplying, I get 2 times the big perimeter equals 3 times 17 is 51. And so the perimeter of the big one is 51 halves, or 25.5. Whoa, 25.5. Okay, next one here. Whoa, this is crazy town. Okay, we want to find the perimeter of triangle CBH. So CBH, this triangle right here. And it says these triangles are similar, and which ones? C goes with F, so C and F, and B and E, so B and E, and then of course the vertical angles match. Okay, AD is parallelogram. I don't know why we need that information, but thank you. And then we got everything written in there. CH is 7, FH, FE is 11, EH, great, okay. Well, the perimeter of this one is 10 plus 11 plus 6. That's 21 plus 6, that's 27. And so then we know the ratio from this one to this one. So from CH, so side CH corresponds with side FH. So over here, FH is 10, corresponds with 7. So from big to small, it's 10 to 7 is perimeter of the big one, right, which I'm going to erase, is to perimeter of the small. But I know the perimeter of the big one is 27. And so then I can just solve. So 10 times perimeter of the small equals 7 times 27. Yeesh, that's going to be something big. Okay, let's see. That's 140 and 49 is 189. Oh, that wasn't so bad. And then dividing by 10, we get 189 tenths, or 18.9. Very cool. Okay, last one. This is a cool problem, and I'm also going to end on this in just a couple seconds. So here's a really common type of problem next chapter. If we have a right triangle and then we have an altitude drawn, what we actually get are 3 similar right triangles. And again, I'm going to talk about this down below. But we have this original triangle that has angle A there. And then that's going to be similar to this triangle that also has right angle and angle A. But if we look at this as angle B, well, this triangle's got angle B, and that's similar to this triangle that has right angle and angle B. Oh my goodness. So the angle markings help navigate this. And so here we have 5, and that's it. That's all we've got right there. And so we want to find the perimeter of the big triangle. And so we know, now we really in this case don't care about this version of the triangle like this. We don't care about this one over here. We just know, well, in the small triangle, the perimeter here was 3 plus 4 plus 5. So the perimeter of 7 plus 5 is 12. Okay. And we know that this side on the top between angle B and right angle is the same as the 3 here that's between angle B and right angle. So we know those two go together. So the ratio of big to small, so the perimeter of the big to the perimeter of the small, is in a ratio of 5 to 3 because those sides correspond. And so then we go down here and we go, well, we know the perimeter of the small one is 12. So I'm going to go ahead and erase that and put a 12 here. And then we just multiply. So we get 3 times perimeter of the big equals 60. And so dividing, we get perimeter of the big one must be, I couldn't do math there for a second. Perimeter is 20. Or what we could have done is said, well, if we got from 3 to 5 there, then what would this side be? And what would this side be? And we could actually solve for those side lengths and then add up the actual values, right? This was just a shortcut saying, well, that we know the scale factor is 3 to 5, and so we could scale factor up the perimeter. All right, so let's do this problem. This one again is we've got an angle bisector just in one triangle. We don't have similar triangles here. So what we can do though is say, well, this angle bisector cuts this other side so that these are proportional to these. So we get x is to x plus 3 as 4 is to 6, right? Going from the segment to the side, segment to the side. So cross multiplying, we get 6 times x equals 4 times parentheses x plus 3. So 6x equals 4x plus 12. So subtracting, we get 2x equals 12, x equals 6. Woohoo! Now let's just plug it in. We'll get 6 to 9. And yeah, that's a 2 to 3 ratio here and a 2 to 3 ratio there. All right, last one. This is when it's saying this is an altitude. Make a conjecture about x, y, and z. So the big idea here is we have this big triangle, A, C, B, which is similar because it has angle A and a right angle. That's similar to this top triangle. And I'll draw it the way it is. So it'll be confusing for now. But I just want to be really clear about which triangle I'm talking about. So angle A, that's D, and that's C. So those two are similar because they both have angle A in them. No argument there. And they both have a right angle in them because anytime there's a right angle here, there's two right angles. Okay, but separately, we also know this big triangle is similar to, and I'm going to draw it also in the way it's pointing. We know it's similar to this triangle, DBC. And the reason is that triangle has angle B and right angle, and the big triangle has angle B and right angle. So all three of those, so anytime you have a right angle and you draw the altitude to the hypotenuse, it actually cuts it into two tiny triangles that are similar to the larger one. So now I can just put in values. I can say, all right, well, in this triangle we had x and z. Okay, and in the big triangle we have x plus y. And in the and that was the only ones. And then in this small triangle down here we had y and z. So the question is, how could we relate these? Well, the way we could relate them is with these two triangles. So if these two are similar, the transitive property of similarity says these two are similar, right? And again, it's because they have a copy of angle B. So we could just use the third angle theorem to say, okay, so if these two match, whoops, sorry, wrong two. If these two match, then their third angle matches. So this one's the 2 arc, right? And then we could say, okay, similar third angle theorem for the other two triangles. If they both have the right angle and the double, well, then their third angle is the same. So this one has a 1 arc angle there. So that just might help you with the markings of the triangles. So now what we do is we go, okay, well, what do we know then? We know that let's go this triangle to this triangle. So y is to, so between the 2 mark and the right angle is to z, okay? As, and going the same direction, z, which is between the 1 arc and the 90, is to x, which is between the one arc and the. So it's saying make a conjecture about how these are related. So there's how they're related. Or if you wanted to, you could cross multiply and say xy is equal to z squared. So either one of these, this is always true. And we'll talk about this in the next chapter. But just a cool thing to add to the end of the video there. All right, hope you enjoyed it. Good luck.